How fast can I make a given Python program? Well, you can get things pretty fast, but obviously it's never going to be as fast as, say, something in a lower level language. But it might not matter in the long run. And what does matter is that we can determine if one thing is actually faster than another. And today we'll be discussing just that, the topic of timing, profiling, and a little bit of optimization. These are two slightly distinct but related concepts. In order to navigate all of this complexity that we have when it comes to timing code, do I need to time the startup of Python? Do I need to time just the code execution? Is there something more surgical I need to do? Or do I just want to time a bunch of different processes? Well, we're going to cover all of that. We have a lot of material here, and we're going to be covering things like the tooling you might use, a little bit of the theory that you'll encounter, and then finally some applied problems. In this segment, we'll be talking about tools. And we have a lot of different choices when it comes to measuring performance in Python. But before I get too involved in all of the different neat tools that we can use, I want to talk about something a little bit more broadly. That's this idea of instrumentation versus development. It's why do we even time things in the first place? And the first thing we'll be talking about is instrumentation, which, as you can see here, instrumentation completely revolves around the interest in the total duration of some unit of code, whether that is an entire program running or that's just timing a single function in Python. This has some very interesting consequences that we might orient our future writing of code or the choice of lower level library that we might want to use. Additionally, we'll usually time things for development purposes. Typically, we'll be using this either to make program design decisions, or probably more likely, we'll be using this to guide our debugging efforts. So a lot of times we'll be talking a little bit about performance regressions. Oh no, I made a commit, and then all of a sudden my program's running a little bit slower, but then maybe 5 other people made commits, and now I don't know which one was the one that actually introduced the performance regression. That's all about development. So let's go ahead and get started with instrumentation. We have a number of different ways that we can time things within Python, and you'll see me using this time module a lot here. And so the first way, if you've ever read any blog post possibly in the world about decorators in Python, they all start off with this, in my opinion, slightly useless example of a timing decorator. And so what you can do is you can write a decorator, right, that takes a function, and then you'll want to execute that function, but before you do that, you'll want to start some type of timer, and then you'll want to capture that result and maybe print it out here. And so what you can see here, I just have a very silly little program. I have function A that sleeps for half a second and function B that sleeps for 2/10 of a second, and I'll call them both. And when I finish, I'll go ahead and print out done. You can see in just under a second's time, my program completes, and I've called both A and B. If I add my timing decorator, we're going to get a nice little message printed out about how long A ended up taking. You can see that it took, right around half a second, which is how long we slept for, so that makes sense. But how often is it that we want to simply time the execution of a function every single time it's called? If we have a much larger program, you might envision that A could be an important function, and it's going to be called a multitude of times. Do we want to time every single time it's called? If not, maybe we would need to spruce up this decorator a little bit more, maybe add a global max number of calls that we want to actually record or report on, because we don't want our standard out to get kind of bogged up with a lot of printouts of timing. But this is a very simplistic approach to timing that works quite well if you want to time a single function. Typically, when we talk about timing, we're talking about units of code, and functions are one of the fastest and most simplistic ways of creating a unit of code that we can do something with. And so the decorator is a natural approach there. But what if my code that I want to time is not written as a function already? What if I want to time both A and B, but not separately? I want to time them both together. Well, the decorator approach doesn't really work here. Instead, I would use something that we refer to as ad hoc timing. And this is a slightly different approach, right? Instead of using a decorator, we're now going to be using a context manager. And with this context manager, we can simply time how long something took to execute within the body of the with statement here. So what does this mean? This means I have the ability to time any amount of code that I want, and it's not terribly invasive. All I need to do is maybe import some utils library, right? If I have this timing context timer here wrapped up in a function, I might import this, and then I might find some area of my code that I want to time, and then I would simply, right, call all of that code in here. But I've now shown you two different ways that require the modification of the program in order to actually time it. And now this might not be what we always want to do, because you can envision maybe I have a long running program, and maybe there aren't very well defined places where I want to time all of these things. Maybe I just want to time specific functions, but I don't want to time that function every single time. What if there's a even better approach? Well, the next approach that we'll be talking about is kind of like setting timing flags, and we'll be using a mixture of our decorator as well as a context manager. And in this context manager, what we're going to do is we're going to tap into Python set profile. And if you're not familiar with this, it's from the sys module, and all Python is doing, we can do this in Python very easily, I should say, because Python will emit events for pretty much every bytecode that it runs. Not every bytecode, but a lot of them. And we can actually hook in and perform actions on those events. We can actually change function calls, we can change code objects. There's a lot of very fun dynamic stuff that you can do here. But what we'll be doing is whenever we activate this context manager, we're going to pass in one or more functions. So in this case, I'll pass in my function A. That hits this timer decorator, or that hits this timer context manager, I should say. We then watch all of the code objects attached to those functions. So we're watching the code object for A because, and the reason we do that is when we use the set profile, there's a very well-defined function signature for these. We get the frame, we get the event, right? This event will be like, is the function being called? Is it being returned? Is it a C function being called? And there's many different events that we can profile here. And then we'll get some arguments that are being passed with it, like when I return true, the argument is true in this case. But the very neat thing that we can do is we can hook into this and we can say if a function is being called and it's one of those functions that I passed in, one of those functions that we want to watch, well, I can start a timer for that, and I can record that starting point of that timer. Then, the next time we get a profile call and we get a return, then we pop out that start time and we simply just record how long it took to run. And so what you can see here is when I run this chunk of code, we'll just need to pass that args. Very good, just delete this here. We end up timing the execution of A only when it occurs within our context manager. And so what you can do that's very neat with this is if I am using some higher level function, right? It's Python, we have functions that end up calling other function or other methods attached to other objects. All I need to do is I don't need to go in and change any of the source code. I can simply say, watch this specific function or watch this specific method. In this approach that I've showcased here, right, it's not perfect. If we have a recursive function call, this will actually start to break down a little bit, but the idea still works. I can pass in any arbitrary function or method that I want to in here, and my program will automatically look out and record just those function calls. So if A ends up calling B, right, and I only watch B, well then I would actually end up recording B here. And so we can actually get rid of this. I'll call B from A. And you can see that I'm recording B even though B is never explicitly called within my context manager. So this is just a little bit more surgical or a little bit more precise of an approach when it comes to just timing arbitrary Python code. But one thing that I want to get to before we talk about timing, well, not just Python code, but code in general, or programs in general, I should say, is this. You've seen me use perf counter. You've seen me use it a lot, actually, in every example we've discussed so far. And I hope you have that question itching at you. Why do we use perf counter? Why not use datetime.now, time.time, time.monotonic, time.process time, time.perf counter? There's even a threading counter as well, or threading time, I should say. But with all these choices, how do you know which one to use? Well, I'll give you this. Time.time and datetime.now are based on your system's clock. Depending on your computer setup, this could be synchronized to some network computer. Mine uses NTP, but that's not always what we want. And I'll show you why here in a moment. Let's go ahead and we're just going to run a quick test using all of these timers, which are all available, or I should say all of these clocks, which are all available in the time module. And so we're just going to quickly just run a little test here. And all I'm going to do is 1,000,000 times, just going to evaluate 1 + 1, which even before this hits the Python interpreter level, right, we've seen that this is actually folded into a constant and it's just 2. But how long does that take? To do 1,000,000 additions, or to perform 1,000,000 load fasts, I should say. You can see that all of our clocks are pretty similar, right? We got similar timings. It took 0.4 seconds, about 0.4, 0.3, 0.6. And what we have to understand is that these timings will shift around, right? My machine might not be under the same load at any given moment. You're actually going to see these timings shift about every single time that I execute this. And in fact, this is slower than when I was originally testing because I'm running some more background processes than I was yesterday. So this is a simple way that we can test all of these clocks and start to determine, are any of them different? And so instead of performing 1,000,000 computations or 1,000,000 load fasts here, what if I just performed 1? And you can see that when we perform just a single load fast bytecode, what we're getting back out is pretty similar. The thing that I want to point out is that our perf counter seems to be just a little bit lower than all of these other values. One of the reasons we might think why that is because perf counter is actually, supposed to be linked up to a very high resolution clock, which we'll get to in just a minute. But what I want to share with you is that each of these clocks has a different purpose. The time.time is used for reporting dates. The time.monotonic is a monotonic clock, and what that means is it will never go backwards. Whereas you can think time.time, well, if it's based on my system's clock and that's synced up maybe to a network device, or maybe it's just running on its own, if I change the date on my computer right in the middle of calling time.time, you can think that, or maybe, not if I don't manually change the date, but if I happen to be timing a long-running process using time.time or a long-running Python function, and I'm running it at midnight and daylight savings is coming up, you can think of the disastrous effect that that would have because daylight savings will change our computer's clock if we're linked up or synced up to whatever network we're using. Then our time.time timer will be completely off. Will either be an hour ahead or an hour behind, and you can think of the very disastrous effects that this might have on your actual estimates of timing. Our monotonic and our perf counter timers are actually quite similar. They're both counter clocks that will not go backwards. But the very interesting thing here is that if I print out time.time, this number actually has a meaning. This number is the Unix timestamp for right now. Whereas if I do something like this, if I start a monotonic clock, this number actually has no meaning to it. The monotonic, the performance clocks that are being used are effectively only useful in a relative comparison, meaning I would have to subtract one monotonic from another in order to find the elapsed. It does not have a meaning for any start time. The last clock that's here is that process clock, that process time. And all this is doing is actually measuring our CPU time. And so it's the time spent when we're actually performing computation or work. And you can see here that sleep obviously suspends that work. And so we're not capturing any time. And this could be definitely something desirable if you want to measure more specifics about how long your your machine is actually doing work for, as opposed to maybe how long it's waiting on something like a network request.